So we now have Kepler's 3 laws that explain very well every observation about the planets that were made by humankind at that time. And humanity still considers the geocentric model as the leading model of the universe, or whatever the observable universe was at that time, with the naked eye. All right, so that was the question. Which one is the model we should consider to best represent the world we live in? So the thing is, there are still 3 key objections that are rooted in the Aristotelian view that argue for that kind of thinking, that the fact that the Earth must be the one at the center and not moving around the sun, right? And one of them was that the Earth could not be moving because objects in the air would be left behind, right? And we all know that, things are still living, sitting on the surface of the Earth. The other one was we have no reason to not believe that heavens should be perfect. And so why should we consider non-circular orbits when we know, the heavens need to be perfect? There's a lot of perfection out there, or isn't. And then the third was, hey, if the Earth were really orbiting the sun, then we would have detected stellar parallaxes by now. So the doubters were just not being unreasonable, isn't it? It looked like it. And it did look like that until we gathered a lot of evidence to overcome those doubts. And a lot of evidence came from Galileo, who was the one not to invent the telescope, but the one to first point the telescope to the sky. He also ran a large series of experiments, and he was maybe the first bona fide physicist, as he looked at how things move, at why they rest, at how motion happens, and what causes it, and found, for example, right? So first objection, remember? People said, well, things should be left behind, they fall behind if the Earth should move. But Galileo's experiments show that the objects in the air would actually stay with a moving Earth. Aristotle thought that all objects naturally come to rest, but Galileo showed that objects will stay in motion unless they force act to slow them down. And of course, all these. Actually, a lot of examples. You're traveling by bus or by plane, and even though those things are moving along on the surface of the Earth, you're not falling behind, right? You do have that feeling just at the very beginning, but that is because there is a force that acts on you to take you out of the rest, right? So they all kind of make sense now after we run all these experiments and understand, right? So you don't actually feel anything that would hold you forcefully in the airplane, right? It's not to fall behind. Okay, so that thing is actually called inertia, and this is a concept that Galileo was one of the first to think it out. Galileo also proved in quite a few times that the heavens are actually not as perfect as we might have thought. And the thing is, I mean, it was Tycho's observations of comets and supernovae that already challenged this idea, but then using his telescope, Galileo saw imperfections on the surface of the sunspots, about which we will learn in a whole chapter that we have about the sun, our own beautiful dear star. And Galileo also observed the mountains and the valleys on the surface of the moon. Here is a beautiful image of the surface of the moon. Of course, the one made of cheese, right? Because it does have those holes in it. No. Okay. Yeah. So so these are some of the imperfections, right? And remember the third objection, the lack of measurable parallax. All right. Well, by using the telescope, he also was able to actually kind of resolve all that Cara Lactee, the Milky Way, basically, which seemed to be just a band, white, something, with the telescope. Actually, if you get to take a look at that, you can see that that is actually made out of many, many, many white dots. And those are stars, right? So basically, with the telescope, Galileo was able to show that stars actually are much further than Tycho Brahe thought, and of course, if they are so far away, okay, then it makes a lot of sense that we were not able to measure the parallax, especially with the naked eye. I mean, even with the telescope that Galileo Galilei had, he was still not able to measure any parallax because that telescope was just not powerful enough. The stars are really that far away. All right. Also, Galileo proved even more than this. So the proof that came by just pointing a telescope out there was amazing, basically. So the main objections were overcome, and beyond that, Galileo was also the one to discover that there are other cosmic objects that revolve around other planets, not the Earth or not even the Sun. Here's an example of the discovery by Galileo of the 4 moons that orbit Jupiter, right? So he discovered, right, so this is Jupiter, and he discovered and took note over many nights, okay, that there are these things, okay, that are moving around, basically around Jupiter, okay. He was able to resolve those satellites, okay. And if you just kind of write down, I don't know if you can copy and paste this URL, you can see a beautiful time lapse of about 3 hours of moons orbiting Jupiter, obviously not Earth, which is condensed into about 10 seconds. And it's beautiful, and it's taken with an amateur telescope, and it's just amazing to witness. Here's a photograph of Jupiter and the Galilean moons. So Io, Ganymede, Europa, and Callisto. I can check on that and let you know. That's, as I said, things that happen inside the solar system are the subject of another class. All right. Hey, here is actually another very important observation that brings serious support to the sun-centered model. What do we have here? The phases of Venus. So Venus is not just a point, a dot out there with the telescope, and albeit these are beautiful images not taken with the telescope that Galileo Galilei had. This is a much better telescope, from this observatory, and so here's what even Galileo was actually able to see, that sometimes Venus looked like a crescent. So very little was actually of the planet Venus was illuminated by the sun, and sometimes was a gibbous, almost a full Venus here, right? Also, if you look carefully at this image, right, you see that the size of Venus, right, so this is a tiny Venus. The size is different, right? So when it is a gibbous, then it is tiny. And when it is a crescent, it is huge. Well, larger, much larger than when it is a gibbous. All right, so the thing is, in the Ptolemaic model, where the Earth is at the center, an observer from Earth would never actually be able to see the illuminated side of Venus, or it would never be able to witness a full or gibbous Venus. All right, all of these phases are actually simply present and simply explained only when Venus goes around the sun. So this is Venus. Around the sun. So the blue dot would be here, right? So here would be Earth with Earth's orbit around the sun, okay? If these things, so this is Earth in the, so this is the geocentric model, and this is the heliocentric model. So you see, in the geocentric model, we would never, so we look at Venus, and you wouldn't only be able to see a crescent Venus, never a gibbous one. While in the heliocentric model, you actually get to observe all phases. And also, you see, the full one, or the gibbous, would be further apart further from the Earth, while the crescent, look at that, it's closer. Which is matching very well. Matching exactly, actually, what Galileo observed. First, of course, now we also observe all these things. All right, so it might seem to you, I hope, to me at least it does, that the scientific case is settled. We did have plenty of evidence for the fact that the heliocentric model matched the way the universe behaved, and it should have been the case, scientific case, when Galileo brought forward all of these findings with clear arguments against a geocentric universe. Nevertheless, politics, maybe just like today, unnecessarily complicate the story. So what happened? The Catholic Church ordered Galileo to recant his claim that Earth orbits the Sun in 1633. His book on the subject was removed from the Church's index of banned books only in 1824, so hey, almost 200 years, okay? And was formally vindicated kind of like just yesterday. Kind of amazing, isn't it? So you see, science is not that straightforward to do, and doing science can in fact be pretty complicated. Interestingly, actually, defining science can be surprisingly difficult. You know, science comes from the Latin scientia, which means knowledge. But not all the knowledge comes from science. And an example, you know what flavor of ice cream? You like without doing any experiment. You just know it, right? So you see, just knowing something and separating that from science is just not that easy. All right, so you know, the idealized scientific method says that we should be proposing and testing hypothesis, right? Where a hypothesis is an educated guess. It's usually based on observations, right? So usually observe something, ask a question, and suggest a solution or possible a solution, an educated guess, right? But that's a suggested solution. And then you make a prediction or build a model. And then based on that, you're going to perform a test. You need to experiment or make an additional observation to see if that new observation matches the prediction and the hypothesis. If that doesn't happen, we're going to have to change the model, right? If the new data do not match the model is therefore not correct. A new model is needed. Oh, the life of a scientist. If you thought they have it straightforward from the beginning, as the myth seems to be, you found out that that is actually not